So far we've taken great pains to remove the vector from any particular coordinate system. And in this lesson we're going to stick it right back into the coordinate system. And you'll see there's a good reason for doing this. So we're going to take our regular Cartesian coordinate system. We have the origin O, so this is the point 0, 0. X goes and gets big positive in this direction. So here's our x-axis, and our y-axis, our numbers are getting big in this direction. And we've got all four quadrants, but we're just showing this one quadrant in this picture. So what we can do is we can take our vector A and slide it so that the tail is right at the origin there. And because A is a specific length going in a specific direction, there's exactly one point in the Cartesian coordinate system that's going to correspond to that vector if we know that the tail is at the origin. So let's say that point is A1 comma A2. So what we do is we say, okay, any vector that has its tail at the origin, we call that an origin vector. So we write the origin vector A using coordinates. We can say A1 comma A2. Or actually, the vector A in general is going to be defined as A1 comma A2. So the way to think about that is that if we have, we can think of it as a sum of two vectors, one going in the x direction, one going in the y direction, and the little trick that we do here is we say, okay, let's have a vector I that has unit length, and it goes in the x direction. So it's exactly length 1, and it goes in the x direction. If we multiply I by the scalar A1, then that vector A1 times I is going to be exactly the length of A1, and it's going to go right along the x-axis. And then if we have a vector J that has exactly a length 1 going in the y direction, and we multiply that by A2, by our y coordinate, then we're going to go up exactly A2 in the y direction. If we add together A1 times I plus A2 times J, we get our vector A again. Okay, so and we can rewrite I as these angle brackets 1 comma 0 and J as angle brackets 0 comma 1. Okay, so and actually, since we know A really doesn't need to be right at the origin, any vector A actually is going to work this way, right? If we go, if we can add together the vectors A1 times I in this direction and A2 times J in that direction, and we'll always get A. So we can write A as A1, A2 whenever the origin vector A has its head at the coordinates A1, A2. Okay, so the idea then is A1, A2 with the regular old parentheses indicates a point on the plane. When we have the angle brackets, then we're talking about A1 times I plus A2 times J. We're talking about the vector. Okay, so and that's the vector that, you know, if we started at the origin, if we put the tail of the vector at the origin, it would go to the point A1, A2. And then when we have a vector A equal to A1 times I plus A2 times J, we call A1 and A2 the components. And these components are scalars. Okay, A1 by itself is a scalar. You have to multiply it by I to get this vector A1I. And the same thing with A2. It's a scalar. We multiply it by J and we get this vector. Let's see, we also talk about if A1, A2 is the point P, we also talk about the vector P or OP as the vector from the origin to the point P. I think there was another point on here. Oh, a couple more points. Let's see. Oh, yeah. Yeah, on the blackboard we usually draw, have an arrow over the vectors. We talked about that before. And in text you'll usually see it in bold. And then, let's see. Oh, yeah, any real number is all real numbers are scalars. So A1 and A2 could be any real number, and that makes sense because A1, A2 could be any point in the plane. So we're going to see coming up the point of all this notation and how it can be very useful in geometric calculations.